Jerusalem to talk about the Revo debate, history, and philosophy of science. And once it is possible to be in several locations, at the same time, I would like to participate in this experiment.
So hi, thank you for inviting me. Can you hear me?
Yes.
Especially that you knew in advance that I'm a little skeptical and may answer the question of whether there are scientific revolutions in a sort of yes and no, it depends on the perspective, something like that, as we shall see. And so, thank you, and thank you, everybody, for being here. So, we know that the term evolution had a completely different meaning, right? In the Revolutionaries, in Copernicus' book, he was thinking about the orbits, the revolutions of planets around the sun. And then we have the modern news, which is a complete shake-up, destroying the foundations, building a new building. And I was always wondering how we got from the revolutions to this modern news. I knew Kant was somewhere in the middle, talking about his own Copernican revolution, referring to the original Copernican revolution. But then I found out, and maybe many of you know this already, that in between we have the expression of the glorious revolution coined by a politician. And what did this politician want to say about the glorious revolution? He coined the expression 1 year after it actually happened. That it's not such a big change, it's only a revolution. We are going back to better times. We're going to get rid of James II, and we're going to go back to better times, what we call in Hebrew, להחזיר עטרה ליושנה. So obviously, there are political and cultural reasons for describing something as a revolution in the sense of a completely new start. And the term scientific revolution was also used by historians of science, famously Alexandre Poiret, the Revolution Astronomique, Alfred Repotro, the scientific revolution. Note, 1500 to 1800, very long revolution. We tend to think of revolutions as something more abrupt, right? And as we saw, there are always interests, personal, political interest, and here is something from our tradition. The Talmud wants to present every innovation as if it was already there in the origins. So we say, כל מה שתלמיד ותיק עתיד לחדש, כבר נאמר למשה מסיני, which means every novelty by the brightest scholar was already revealed to Moses on Mount Sinai. Now, the persons who said this did not take it literally, but they want to give it a kind of, or maybe some of them took it literally, but I think it was more to give it the validity. So we have cultural, political interests, we have personal interests, like someone wants to be inspired by Einstein, and another person wants to distance himself from war, etc., etc. And we have self-images of individuals or groups as being revolutionaries or non-revolutionaries. Now, how do we materialize these interests in the way we see or advertise or talk about the events, whether they are revolutionary or not? So, one already said, language. Language is so important in this. So we have the means of expressing the interest-driven perspective by language and description. Duncan and Janssen, in a book called Constructing Quantum Mechanics, to which I will return, and there are the evolutionists, not the revolutionists, they think that historians are more likely to see continuity where physicists see rupture. But we've seen that it was historians like Correa, Patrol, and others, not to mention Kuhn, who talked about revolution. So let me go back to examples of description sensitivity, the way we describe something. So one is from the personal realm, and the other is much more important in science. So if we take Hilary Putnam as an example, I mentioned him at the end because he contributed to a theory of meaning that is related to what we're talking about. So Hilary Putnam was a realist throughout. And so we can say there is continuity. But then he made several distinctions. He had internal realism versus metaphysical realism. He had common sense realism. And sometimes he even said that just realism with capital R versus lowercase realism. So there are all these differences. And his self-image was of someone who constantly changes his opinion and improves himself, and others also see him as a paradigm of continuous change. So description matters a lot. My second example is much more elaborate and comes from the general theory of relativity. And by the way, when you were talking about Einstein, I thought that the revolution in the general theory of relativity, not the special theory of relativity, and I don't think he hated any of those. Maybe he was very critical of quantum mechanics, but he loved general relativity. He said it's extraordinarily beautiful. So, what about the general theory of relativity? So let's say we have an equation and a caveat. Here I'm not talking about a diachronic perspective of different descriptions, different perspectives, but about a synchronic cleavage between different perspectives that depend on how we describe the theory, okay? And the controversies about how to describe the theory. So if we have a simple equation, A equals B, how do we read this equation? We can read it as a reduction of A to B. A is nothing but B. We say temperature is average kinetic energy of the molecules or whatever. We want to say it's nothing but that. And of course, we could read it the other way around as well. But there is a third possibility, neither the reduction of A to B nor the reduction of B to A, but we have here a relation between equally real magnitudes or entities, right? Now, what happened in the general theory of relativity? What happened in the general theory of relativity? We have an equation, which is a little more complex than the previous one. And on the one hand side, the G stands for geometry, and on the other side, we have the mass energy tensor. So on the right-hand side, we have the physics. On the left-hand side, we have the geometry part. But it's not as simple as that. So the first question is, what is the relation? Is there any reduction here of physics to geometry or geometry to physics? But it's more complicated than that, because actually, the left-hand side, what we call the geometry part, has a dual meaning. Because on the one-hand side, we can interpret it as describing the geometry, more specifically the metric or space-time. And on the other hand, the components of this tensor describe gravity or represent gravity. Thank you so much. So we have the equation, but one of the sides has a dual meaning. And we can see how much controversy there is about this dual meaning that depends solely on how we read this magnitude. Do we read it as gravity? Then it's one thing, perhaps more continuous. Do we read it as a rival revolutionary geometry? It will be more discontinuous. So here's Einstein. According to the general theory of relativity, this is in the 1916 paper, the paper about general relativity published about all these difficulties with getting to the equations. According to the general theory of relativity, gravitation occupies an exceptional position with regard to the other forces, particularly the electromagnetic force. There were no other forces at this time, since the 10 functions representing the gravitational field at the same time define the metrical properties of the space measures, the wave of gravitation and the metrical components, which is geometry. And the dual meaning of the metric tensor is at the core of GR, and again I can refer to the previous lecture, talking about redshift, time changing or slowing down. For example, the gravitational redshift can be interpreted as indicating either the variation in the metric, so space-time changes and therefore time changes from one point to the other, or the slowing down of clocks under the influence of gravity, which is much more similar to the previous intuition about gravity doing something to matter, and if matter becomes similar to other physical parameters, maybe gravity can do something to time as well. It's still revolutionary, but it's less revolutionary. And the merger of gravity and geometry means that the transition from the special to general theory of relativity is a transition to a dynamic space-time. Again, we heard a little bit about that. A space-time that is itself shaped by matter and fields. And there is a very famous quote from an enormous book by Meisner, Thorne, and Wheeler called Gravitation, just one word, but 1,000 pages. And they say, you may have heard this quote, space acts on matter, telling it how to move. In turn, matter acts back or reacts back on space, telling it how to curve. And they see this relationship between matter and space, this dual interaction between them, as the main innovation of general relativity. Nowhere, this is still a quote from their introduction, nowhere does Einstein's great conception stand out more clearly than here, that the geometry of space is a new physical entity with a dynamics of its own. But not everybody agrees. Steve Weinberg, in '72, also a great physicist, thinks that there is a problem with the geometrical interpretation because of discontinuity with the other forces of physics. I believe that the geometrical approach has driven a wedge between general relativity and the theory of elementary particles. As long as it could be hoped, as Einstein did hope, that matter would eventually be understood in geometrical terms, and it's true that at a certain point of his life, Einstein thought that that would be possible, it made sense to give Riemannian geometry a primary role in describing the theory of gravitation. See how he calls it, theory of gravitation. But now, the passage of time has taught us not to expect that strong, weak, and electromagnetic interactions can be understood in geometrical terms. And too great an emphasis on geometry can only obscure, and this is the important part for me, only obscure the deep connections between gravitation and the rest of physics. So depend on our perspective on the theory, whether we see continuity or discontinuity. So he wants us to forget about the geometric analogy and focus about gravitation. But there are others, for example, singe. If I break my neck by falling off the cliff, my death is not to be blamed on the force of gravity. What does not exist is necessarily guiltless, but on the fact that I did not maintain the first curvature of my word line, exchanging its security for a dangerous geodesic. So, no gravity, only geometry, no geometry, only gravity, and then we have people like Kip Thorne, who say the flat space-time paradigm laws of physics can be derived mathematically So one can derive from the other. It does not matter. You see in the last two lines, it says the difference between them is like the difference between 0.001 and 1/1000. These are only different mathematical representations of the same number. So this is also one possibility, as I said, when A equals B, nothing but geometry. The other possibility is nada but matter and gravitation also with the force, with the other physical forces. And then we have this idea of equivalence, which Richard Feynman also shares. I think all of them were revolutionaries, really, if you ask me. It is one of the peculiar aspects of the theory of gravitation that it is both a field interpretation and geometric interpretation. Okay. So what happens in the history of science? We know already that there are revolutionaries, like, or people who believe in revolutions, like Kuhn. And that more and more people nowadays are becoming skeptical about the concept of revolution, and we'll hear more about it during the conference, I'm sure. But I want to mention two very recent books. One is by Hanoch Gutfreund of Hebrew University and Jürgen Rehn of Max Planck in Berlin, called The Einsteinian Revolution. It's an ironic name because they want to show that actually there was no Einsteinian revolution. And the other is really monumental, by Duncan and Janssen, Michael Janssen, Constructing Quantum Mechanics. 2 volumes on the history of quantum mechanics. Amazing book. So what are the concepts that they use instead of the concept of revolution? Rehn and Gutfreund talk about the transformation of knowledge systems, a little similar to what you said. The knowledge was there, but it was just kind of shifting around, which is to me to undermine really the achievement of the Einsteinian revolution. And Duncan and Janssen built upon the metaphor, used the metaphor of a building, the arch and the scaffold. Should I say scaffold or scaffolding?
Use the word scaffold in the title, I think.
Sorry?
I think they use the word scaffold in the
They use, I know, but in general, would you say, I built a scaffold, I built a scaffold? I wasn't clear about that. So that's their metaphor. Meaning that, let's say, the older quantum theory between 1900 and 1925-26 was a scaffold on which the new quantum mechanics of 25-26 by Heisenberg first and then Schrödinger was built. And by the way, again, I don't think Schrödinger, it's the equation, not the cat. The cat is also important, but Schrödinger's equation is the important part of what Schrödinger did. And many people think it's revolutionary in the sense that they cannot trace the steps that led from classical physics to it, and other people want to trace the steps and see it as less revolutionary. But again, a lot depends on the description. So, how do Rehn and Gutfreund describe the aim of their books? They say the main goal of this book is to dispel the myth that Albert Einstein, the unconventional scientific genius, instigated an overwhelming scientific revolution through pure thought alone. And historians among you will recognize immediately the romantic image of the genius, right? Lonely, doing everything on his own, ignoring society, ignoring conventional norms in music, especially in music, but in science too. When Einstein fitted this romantic ideal in many ways, walking barefooted and playing the violin and on the boat, etc., no haircut. So, so they argue against this image of Einstein. They're not the first to be skeptical about this image, but that's their idea. And what else do they say? The process of transforming or restructuring existing knowledge can be described as a Copernicus process, Copernicus created a new astronomical system by shifting a formerly peripheral celestial body, the sun, to the center. Rather than starting with the tabula rasa, he essentially adapted the complex mechanism of planetary astronomy inherited from Greek and Arabic astronomy. So he only adapted, not a real revolution. And the same about Einstein. The substance of Einstein's work was not new, but rather was the result of an accumulation of knowledge over centuries. It was his conceptual organization that was new. So not the material, but the conceptual organization was new. But is that not a revolution? So it's really tricky. And they even see general relativity in a sense as a partial return to Aristotelian physics, because they think that the motion in the space-time of general relativity is a little bit analogous to natural motion, a concept that Aristotle had and the scientific revolution got rid of. So they go as far as saying that. By the way, I think Kuhn has something similar somewhere. And they portray Einstein as a scientist, and pay attention to this quote because there's a twist. They portray Einstein as a scientist who helped bring classical mechanics to its completion. Again, connected to the previous lecture, to its completion. Physicists think of theory of gravitation as a classical theory versus quantum mechanics, which is completely non-classical. So he brought classical mechanics to its completion and thereby contributed to the shake-up of its foundations. Now I think shake-up of its foundations is pretty much a revolution. And yet, they say general relativity is the work of a single person who took a stand against the trend of contemporary physics. So it was a revolutionary, it wasn't a revolutionary. No. At the end, I'm not sure. Okay, now this building metaphor. It's not completely new, even if the terms arts, scaffold, so on, not using the same word, but the idea that in order to base knowledge on a solid foundation, what do we have to do according to Descartes? We have to destroy everything. We have to clear the ground. We have to forget everything that we knew, right? And then we have to start from very, from clear and distinct ideas and so on, and build on this solid foundation. We can build the structure of knowledge. But even empiricists, some of them share the idea that we have to forget everything that we knew. And when does this idea mostly criticized? It was criticized by American pragmatists. So 19th century American pragmatists really revolted against this epistemology of the 17th century. And here's Peirce in an 1868 paper on some consequences of foreign capacity. We cannot begin with complete doubt. We must begin with all the prejudices which we actually have when we enter upon the study of philosophy, but philosophy including natural philosophy. These are prejudices not to be dispelled by maxim. Cannot tell people, be skeptical, forget, ask, doubt. This is not done by a maxim. You have to have a problem here and now that engages you. These are prejudices not to be dispelled by a maxim, for there are things which it does not even occur to us can be questioned. Hence, this initial skepticism, meaning Descartes' skepticism, will be a mere self-deception. And here is James, his fellow in founding pragmatism. The point I now urge you to observe particularly is the part played by the older truth. Older truths are important. Their influence is absolutely controlling. Loyalty to them is the first principle. In most cases, it is the only principle. This is not a normative, this is a descriptive. Most people usually obey or are under the spell of the older truths. But James now says, but often the day's contents oblige a rearrangement. So he too talks about the transformation, the rearrangement. The term revolution doesn't appear there. And how is this rearrangement done? In your opinion, counts as true just in proportion as it gratifies the individual's desire to assimilate the novel in his experience to his beliefs in stock. Those of you who are familiar with Quine, there is a very similar idea of minimum mutilation. You reorganize the web of belief, but you try to harm as little as possible the older parts of the web that have worked so far. Now these people, Duncan and Janssen, and Goodfriend and Wren, use biological analogies, and that's why the title of my talk was Revo-Devo, alluding to the Revo-Devo. So they use biological analyses, evolutionary analogies, and the Revo-Devo analogies in the continuity promoting approaches. Goodfriend and Wren don't go into much detail with this analogy. They just want us to acknowledge that gradual small changes lead to new structures. Duncan and Janssen, however, go a little more deeply into the analogy, and they actually talk about Revo-Devo as an analogy. And the reason is that they want to emphasize the generation, emphasis on generation of variation rather than on selection. There is selection, they don't counter or critique natural selection, but they think that as in Revo-Devo, we have to look at development. And so they want to look at generation, and furthermore, following Gould and Levontin, Duncan and Janssen emphasize constraints, which they find in previous theories. So previous theory serves as a constraint. You cannot go anywhere wildly. You are somehow constrained by the previous path that has already been taken. But there is also a clear disanalogy, because when you want to build an arch, you build a scaffold that will enable you to build the arch, right? But in science, the new theory cannot constrain the previous one. So the scaffold, the older theory, is not built in view of the new theory. This can hardly be imagined. So the analogy is powerful, but it has its limits, as most analogies do. But I want to go back to philosophy. After all, I'm a philosopher among many historians, so let me go back to philosophy a little bit. What are the philosophical implications of the debate? We know why it should matter to a historian. If a historian believes in continuity, and I think it's really great fun to go as a detective through all the steps that led to a new theory. But in philosophical terms, does it really matter so much whether I call it a revolution or an evolution? So we have to go back to Kuhn, and I want to distinguish three levels of Kuhn's argument that are not distinguished in the book, but they are all in the book. The first level is a historical level. Historically, he says, in each period, we have one paradigm governing a discipline, and there's no dialogue between different paradigms. I think historians have contested this idea and have shown how much dialogue there has indeed been between different dialogues. So I don't think the historical argument is very well founded. On the other hand, there is a psychological cognitive argument. And this argument, this second level of Kuhn's book, tells us that we cannot but be constrained by our present ideas, conceptions, theories. And unfortunately, here now, after 2 years of war that started because of a wrong conception that every fact was fit into it, erroneously and deceptively and terribly, I think we must acknowledge, not only in science, but in general, that the psychological cognitive argument is very sound, and that we should be alert to its dangers as far as we can be alert to them. And the third argument is the one that really troubled philosophers very much, and it's the linguistic argument. And this linguistic argument can be summed up in one word, which is incommensurability. Why do philosophers think that incommensurability is so important? Because if we take it seriously, different theories cannot talk to one another, we cannot compare them with reality, we cannot compare them with one another or with reality. There is no idea of one theory being better than another. Why should we abandon one rather than the other? We abandon theories just as we convert to a different religion for no rational reasons. The whole rationality of science collapses. So philosophers think that incommensurability is a real danger. There's an argument here that should be answered. And what is worse is that it's very easy to get to incommensurability in two very simple steps. Intuitive steps, we heard about intuition already, but these steps are very intuitive. The meaning of most scientific terms is determined by the theory that employs them. If you want to know what entropy means, we have to study statistical mechanics and to see what entropy means, right? So meanings are a function of theory, and meaning determines reference. It should be determined, not determined. Meaning determines reference, because what entity do we talk about? The entity that is described such and such. And from here, we can say the change of theory leads to change of meaning, because meaning is a function of theory, and change of meaning leads to change of reference, and thus we get to the picture that different theories refer to different entities or even to different worlds. That is, we have incommensurability. These two theories are two monads, no dialogue between them at all, and no dialogue with reality. But what we do want, and what as scientists and as lay people, we usually assume that two different theories describe the same world. And therefore, they are the same entities there. There are atoms out there. Are they divisible? Are they indivisible? Do they have electrons orbiting around them like planets orbiting the sun? Or are they quantum orbits that obey completely different rules? So what do we do about that? How do we save the intuition that different theories refer to the same world? Putnam tried a bold way to save realism, to save the possibility of talking from different perspectives about the same world. And his theory of meaning is called externalism. And as he famously said, meanings just ain't in the head. And what it means is that different theories can refer to the same entities. And as many of you may know, he also has a parallel converse argument in a famous twin earth paper, The Meaning of Meaning, where there is this twin earth thought experiment, where he says that people can have identical mental image and still they're not talking about the same thing because the entity in the world that they're pointing at is not the same. But how do we point at entities that are in the world? So the first idea was that the causal relation helps us to point at a particular thing. This is water. The water I drank quenched, how do we say, quenched my thirst. So there is a causal relation here. But the causal relation works for some entities better than for others. Maybe today we can talk about causal relations with electrons, causal relations maybe even with black holes in a way. But what about very abstract scientific concepts like entropy? Do we refer to something when we talk about entropy? And I think in general, there is no good philosophical solution to the problem of reference. Many people take it as a primitive term. There is such a thing as reference, and we talk about the same world, we share the same world, it's intersubjective, all these kinds of expressions. But I don't think there is a good theory of reference that solves all the problems that this notion arises. So this is where we stand with philosophy. And with history, again, as we go from one case, yeah, I'm finishing, as we go from one case study to another, there is a lot of interesting work to do. But if you want a general concept of revolution, I think at the end, as I said at the beginning, I haven't changed my mind since 30 minutes ago. It's a matter of perspective. And here is Steve Shaping in his book about the scientific revolution. There was no such thing as a scientific revolution, and this is a book about it. Or, if we want to go further back, here is Shakespeare. A rose by any other name would smell as sweet. Thank you.
So we have time for one question. I was doing a bad job as the chair of this session because we are a bit late and the coffee break will be shorter. Yes, please.
I want to ask about the argument that the new theories are constrained by the old theories, and to claim that it's not the old theories that are constrained by the experimental facts that the old theories were consistent with. So the concept of quantum mechanics or the concept of general relativity do not degenerate to the old concept, but you have to show that the mathematics, the description, does give the old experimental facts that the old theories were consistent with.
Sure, that the new theory has to reproduce the earlier results, that's a constraint of theory, but that's not the problem we're talking about. What Duncan and Johnson want to argue is that the previous theory really helped create the new theory by way of continuity. And for example, they think that dispersion results of experiment, as you say, very much led Heisenberg towards his matrices. He didn't know at the beginning that they were matrices, but were really the scaffold on which the arch of Heisenberg theory was built. Sometimes it's experiments, like in this example of dispersion experiments. I think sometimes it's a theory, because if you think of Schrödinger's equation, and I said many people say we cannot trace the steps that led Schrödinger to the equation, but other people say, yeah, look here, he started from the classical wave equation. He wanted to incorporate the Bohr's idea of a wave accompanying the particle. We had the results about the energy spectrum of hydrogen, helium that were already known. So these are the scaffolds that led to Schrödinger equation. So sometimes it's theory, sometimes it's only experiment, but it's not the necessity to reproduce them, but their help in producing the new theory that Johnson and Duncan have emphasized. Thank you for the question.
Thank you very much. Thanks both Yemima and Ron for the excellent talks. We have a 15 minutes coffee break.